Okay, thanks everyone. Yeah, so I am Tracy Becker, and that was a great introduction to a lot of the stuff that I'm going to be talking about. But what we've been working on mostly is a bunch of data that we have in the far and the mid UV from Hubble Space Telescope. And so, as we were discussing quite a bit, there are these different regions of coloration on Europa, and we can see in the visible, we have these dark splotches, and then we have some lighter regions. This is, that splotch on the trailing hemisphere. I want to argue that in the UV, there's a lot that we can do. That was kind of already discussed. There's ways that we can start to try to disentangle what some of these materials are. Of course, we need more studies and, of course, more lab data as well. But what we saw when we started looking in the UV, and this was done by, I got cut off there, Lawrence Roth, when he was looking at the plumes and other features on Europa, this sort of correlation in Lyman Alpha, this bright region here, actually with this dark region here. And so in fact, we actually see where it's dark in the visible, we start to see this brightening effect in the Lyman Alpha. And what I did, and what we did in a paper that we published earlier this year, is we looked at some of those data, actually all of the data that have been taken over many, many years with Hubble, and start to really just try to get that albedo and really focus on making sure we're accounting for any kinds of phase angle differences or actual longitudinal differences. And in the far UV, you can see this green line right here. This was the model that fit best with the data. There is a darkening on the leading hemisphere and a brightening on the trailing, which is usually not what we see in the visible, and it's certainly not what we see even in the near UV. This was work done by Amanda Hendricks. And so you can see that here it's really more consistent with what we're used to thinking about, leading hemisphere being bright, trailing hemisphere being dark. The rest of this in the far UV really is consistent with possibly even being flat or no trend at all between the leading and the trailing. But that Lyman Alpha, we do see that reversal. In other places, like the moon, we see that as well. That is often attributed to some sort of space weathering, or it could be grain sizes. But we do see this reversal, this spectral inversion at Lyman Alpha. For me, what really got interesting when we started looking at this far UV data is that we noticed that 165 nanometers, where we would have expected to see a strong absorption edge due to water, ice, we don't. At Enceladus, this is what this looks like. It's very, very dark in the UV on Enceladus, just like it is on Europa. But as soon as you reach 165 nanometers, you really get that increase in signal, where this absorption is generally accepted to be due to water ice. In fact, when we actually look at spectra of water ice, you get this is what you see. It's very, very bright beyond 200 nanometers, and it's very, very dark shortwards of about 165 nanometers. Even with just a little bit of stuff. So Ujjwal Rao gave me this. You can go see his poster later today and talk to him a little bit about this. But as you add even a little bit of water, you really start to get this water ice absorption edge present. You can change the grain sizes, and that can shift that water edge, but the water edge is usually still there. And so when we looked back at this, we thought, okay, maybe this is kind of the end of the detector, so maybe we're just not seeing it. But we kind of try to put it into greater context. So we put it in a plot with all the other data in the UV that's been collected so far. This is the data that these were kind of our final results, phase corrected, and plotted them on top of Melissa McGrath's trailing hemisphere that she had using the COST instrument on Hubble. And then looking at what we saw from Galileo, this is Amanda Hendricks' data that we normalized it to match this null spectrum, which was taken with Hubble FOS in 95. And so one thing that popped out when we were trying to figure out now, okay, maybe the water ice edge got moved a little bit longwards, maybe it's just really shallow. The problem was that there was no data to really look at it. So we got some Hubble data. We got some observing time last year, and earlier this year we actually got to observe Europa. And so this is what we got to do. We used the Space Telescope Imaging Spectrograph, or STIS, and we had proposed to look at all four hemispheres: anti-trailing, anti-Jovian, trailing, subjovian, and leading hemisphere. Unfortunately, during the leading hemisphere observation, there was a gyro issue, and the observations weren't able to be taken. Hopefully, Hubble's going to come out of whatever issue it's having right now, and we will get that data next year. And so this is just to show you kind of where we were centered on. This is mostly to give everybody a little bit of an idea of kind of the orientation of the slit relative to Jupiter for these observations. And what we did was, because we used the 0.2 arcsecond slit, we would have liked to have had the larger slit and have all of Europa in it, but Europa is actually kind of too bright, and so we were pressing up against global count limits. So what we had to do was we did the 0.2 arcsecond slit, and this is approximately what it probably looked like on the surface. And we just kind of moved it from one side to the other. We did 2 observations like this so we could cover as much of Europa's surfaces as we could. And with that information, this is what the first look. So this is all kind of preliminary. We just got this data a little bit earlier, a few months ago. But the first look was really interesting to me. So this is actually what the signal looks like along the slit. So this is along the slit here. And on the trailing hemisphere first, you can see that we get this increase, this decrease, and this increase. And so that's pretty consistent with kind of hitting one of the poles, going into that dark trailing region that we know about, and then getting back out here to the lighter region again. So this was pretty consistent with what I expected. And then what I was surprised to see a lot of is this really slopiness on both the anti-Jovian and then sub-Jovian hemisphere. So these are from each slit, each observation. And so you really get this kind of interesting asymmetry there. And I think what's happening there is we really are capturing kind of this brighter region at the north, and perhaps getting a lot of that darker trailing stuff in the bottom part of the slit. Yeah, so one thing I do want to mention, though, unfortunately, one of the main reasons we were doing this observation was to really look at that 165 nanometer region. Earlier this year, Jeff Cuzzy published a paper that indicated how STIS has a little bit of trouble when it's not a point source at the shortest end of this detector. So there might be a lot more work that goes into it. The Cuzzy paper did produce a paper of Saturn's rings, even down to closer to the 180, 165 nanometers region, but there's a lot more work that's going to have to get done to really clear out that region. But I don't think that's a huge problem for us. So this is what ours looked like. It does unphysically go extremely high signal where we would expect it to be crashing down low into what we see in the far UV. But as I'll show you later, I think we do have enough information to really start saying something a lot more about what this compositionally could mean for the surface of Europa. So in the trailing hemisphere, and this all goes really nicely with what was being discussed earlier. This is the trailing hemisphere. Whether we're looking just at the dark region or we're looking at those kind of lighter regions, we do see a little bit of an absorption feature right here at about 260 nanometers. And you can see it when we start doing these ratios as well, that's present. That's consistent. I think I show it a little bit later, but with some sort of sulfuric acid or sulfate. And yeah, so I'll show that in a little bit. But just to go through the other data real quick, we also see a pretty important feature there when we ratio the northern hemisphere and the southern hemisphere, or that kind of top half and second or bottom half of that slit when we looked at the trailing, the anti-Jovian and the sub-Jovian hemispheres. So you can really see in that dark region that pattern, that absorption feature is there. So whether we talk about how much of this other material that's on the surface is not the same stuff as a possibly exogenic source, or how we go forward, we have to account for the fact that there is this feature here in all that data. So I promised you guys we were trying to fill in this hole right here. This is what we had, and this is what we have now. So we do have a lot more coverage. We do really fit very nicely over the null spectrum and the Hendrix spectrum. Hers is normalized to meet nulls. Ours isn't normalized. It just plotted beautifully on top, and it fits in with Melissa McGrath. So there's error bars that need to be put on here because it gets a little bit noisier here. But in general, you can see that there's kind of just a continuum. All these hemispheres start to basically meet up at these wavelengths down here, and they just kind of stroll into this far UV. There's no sharp absorption edge that we would have seen with water ice or with Enceladus. And here's what I mean. So here's the difference. So I want to really stress that there are significant differences between these two in the UV. I mean, I don't think anyone's saying that they're very similar at all wavelengths at all, but in the UV, it's pretty striking. Here's that water ice absorption edge at 165, maybe an absorption feature right here, and then continuing back up as you'd see water to go very, very bright at the near UV or visible wavelengths. Europa it's just barely creeping up. And if we look at that at even longer wavelengths, and these are plots from Carlson 2009, you can see that we really don't even reach our peak brightness for Europa until about maybe a little over 500 nanometers. Enceladus, it's certainly a little bit shortward of that. And at 300 nanometers, so right at that cusp of kind of UV visible, we're already at 80% reflectance on Enceladus, whereas on Europa we're at 20%. So it really is much darker for a lot longer on Europa. So here's the spectrum I promised to show, this absorption feature. So Noel attributed this to some sort of SO bond. Amanda Hendricks had done a plot of SO2 frost on water ice and looking at how that kind of fit over the data that they had. And when you look at kind of, if we use the trailing hemisphere, or sorry, the anti-Jovian hemisphere as kind of our normal continuum of this, and then we put the trailing hemisphere here, this band depth is quite similar to what Noel saw as well. So there is an interesting feature here, and determining what that is will also help us disentangle what's going on the surface. Is it exogenic? Is it endogenic? One thing that we started to do with the last paper, and especially in anticipation for the new data, was to see what kind of models we could make that would actually fit over these kind of interesting spectra. Could we make the water ice absorption disappear? The only way that we really did that, at least with these initial models, was if you add water, you can have a decent amount of water, so 75% water, for example, up here, but the grain sizes have to be significantly smaller than whatever it's mixed in with. And when you do that, you do start to deplete this sharp water ice edge. So for example, the purple and the pink right here are the same amounts of water versus some ice tholin, but the grain sizes are different. And so this is the water ice with the tholin and a larger grain size for water, and then this is what happens when you really decrease that water ice side. So you can deplete the water ice absorption edge, but we haven't been able to do that and match everything else. So that's kind of ongoing work that we're going to start doing. And then just to plot a lot of those ideas kind of on top of here, some of these ice tholins by themselves maybe match the shape a little bit more, not necessarily the magnitude, but these are things to start looking at. And like I said, this is all quite preliminary, so we're about to start getting into the modeling phase. So next steps, let's talk about the lab work. So this was the lab work, and so we talked a lot about magnesium sulfate in the previous talk. One thing that I find pretty amazing is that Carl Hippold showed that you basically, here's Europa, are these blue dots, and if you irradiate magnesium sulfate, you can actually follow that pretty well in that near UV into the visible, that really darkening that we see on Europa. Now, does that happen on all the hemispheres? How much radiation do you need? Can different radiations account for the different slopes that we do see between the leading to trailing and the anti and subjovian hemispheres? That's stuff that we should really look at. I think more irradiated salts, different salts, for example, some of the ones that were suggested in the previous talk, that would help us really look at what's going on. Ujjwal has a poster about irradiating salts and ices, so that kind of information will help us really disentangle what these materials are on the surface. There's still a possibility for grain sizes, and we need more lab work. Just as to remind everyone, there is a UV instrument that will be on Europa Clipper, and we will get high spatial and spectral mapping of the surface. One thing that I could imagine this being useful for in this context of this talk especially is that we'll have the high resolution, we'll be able to map out the surface, and maybe regions where we start to see that water ice absorption edge appear, maybe that will tell us something about a more freshly deposited water ice region, and that might indicate regions of interest, that might correlate with maybe a hotspot that we see in the thermal, things like that. So having this UV, having this very sensitive 165 nanometer absorption feature, that it's going to really help us out. We're going to also look for other variations of spectral features, different phase angles, of course. We have all the opportunities of having a flyby mission, helps you get a lot more information, a lot more coverage. And so just for conclusion, this is our final plot that we have right now. Basically in the far UV, it's very flat. Lyman Alpha, we do see that spectral inversion. There's no water ice absorption edge detected on any of the hemispheres, at least. Nothing very strong anyway. If it's anything, it's a little bit of a slope right here, but nothing too strong. Is it due to radiation? Is it due to some sort of lag deposit from sublimation that leaves behind a very micro-thin layer on the surface? Reminder, UV, we're really looking at just that very, very, very top level layer of the surface. We're not really penetrating deeper. So if there's some sort of thin filament that's left behind, that might be what we're sensing, and everyone else is sensing a little bit deeper, different material. Of course, there's the grain sizes that we need to look at as well. But basically, with this data, one of the nice things about doing it with STIS instead of CLAS was so that we could get that spatial distribution information. So we do have something like 40 pixels across the surface of Europa, and we can go through and carefully look at each one of those to really do these comparisons, kind of similar to what was being discussed in the previous talk. We can look at what the UV looks like in these regions that look very clear, or maybe that look a little bit darker, or maybe these regions that maybe aren't supposed to be exactly the same as the trailing hemisphere, but are different and discolorations on the other parts of the surface of Europa, including the leading hemisphere. And so this is kind of our to-do. This is very preliminary, brand new results. So yeah, I'll take any questions.
All right, thank you, Tracy. I'll come around with microphones again.
There's some there.
Go ahead. Okay. A quick question. Are you able to take STIS data and look at just the brightest in the visible part that goes that far spectra, and to look for the UV absorption in the what you would think be the highest albedo reflectance in the visible, so that presumably be the most water rich? And does that look like all the other spectra? Because at 200 nanometers, it looks like everything has the same reflectance, whether it's non-icy or icy.
It starts to look that way. Yeah.
Yeah. So can you do that?
Yeah. I mean, we can't. I mean, with this, we could just kind of single out certain regions that look the brightest. Unfortunately, we don't have the leading hemisphere, which would have been the best case scenario for that. But next year, hopefully, we put in a hopper so that Hubble will go back and observe that, because it was just a failure of the gyro that prohibited us from getting that data.
Thanks for the clarification on that one. And one follow-up question, you mentioned that radiation does affect, or you see only the very, with this UV, very top surface. Radiation affects very top surface comparatively, right?
Right.
Lisier has mapped the amorphicity of the water ice and has shown that a lot more amorphous water ice at higher latitudes, you know, in the leading hemisphere, and Hansen anyway shows that the surface is always amorphous wherever you look. Mm-hmm. So I'm wondering, does amorphous water ice not have this sharp band? Would crystallinity have any effect on the presence of this 165 nanometer band?
I can answer that question. I can answer that question.
Carl,
I can answer that question. There's no difference.
Yeah,
there's no difference.
My understanding, it should be there no matter what we're looking at. But
we have lab data. There's no difference between amorphous and crystalline ice at 160 nanometer absorption.
What causes the band?
That is electronic absorption.
Yeah, well,
electronic excitation.
But some arrangement. What is the what are you absorbing?
In electronic excitation from the ground state of H2O into the first valence excitations. So what happens is the same excitation that is in the gas phase, which is much longer wavelength shifted, starts getting shorter and shorter wavelength shifted as you go from gas phase, water molecule, into liquid water, into solid ice. So this is the blue shift that is caused by interactions between water molecules, but the absorption is molecular absorption, not solid state absorption. So molecular absorption, this is 160, is molecular absorption. And thank you for saying that it is trailing hemisphere. I was shocked because it has to have that sharp feature, even.
Well, I mean, it doesn't. So we didn't get. So this is kind of, this is everything. So we don't have the trailing, we don't have the leading hemisphere in this region that we just did. Yeah. But this right here is the leading hemisphere, and you do see it dropping before we get anywhere near. the far UV.
But you don't know how this would be.
That's
right?
true. We
Yeah.
don't know if there is something that, that jumps up here yet.
So, yeah.
But when we look at what we saw initially that triggered this part of the study, sorry, we'll get there eventually. There isn't that much of a sign of it here either in the far UV data that we have.
So I think this is a very important result, at least from my point of view. I would not have expected it to be like that. Then
I don't think any.
either it should be, as you said, some kind of lag deposit that obscures your absorption, or that something else is actually strongly absorbing, so that water is, So anyway,
I think that's the main argument. And then, what is it? Is it some sort of lag deposit that's more strongly absorbing, or is there just whatever salts that are present? But they have to be more ubiquitously present in that case, because we're not seeing it on the leading or the trailing.
And it is not going to be because of amorphous or crystalline. So that's definitely not going to be the issue.
Just a quick comment on like Murthy said, there's no difference in the far UV between amorphous and crystalline structure. Like I was hoping there would be, but just warming it up from like 90 Kelvin to about 160 Kelvin, we didn't see any changes. So it's not going to help us there. But yeah, I think tonight at the poster we talk about like preferential sputtering and how that can enrich the lag layer and the FUV sensing depth, and how that could suppress or mute the strong absorption.